Right now, without any effort of your own, something holds you gently against the ground, and it feels, for all the world, like a downward pull. Yet that quiet weight hides a strange truth, because the thing we all call gravity may not be a force acting on you at all. In true free fall, with nothing beneath you, you would feel no pull whatsoever, no downward tug, not even the sense of your own weight, because in that falling moment there is nothing there for your body to feel. Tonight, we drift slowly through a single gentle idea that gravity is not a rope pulling you down, but the quiet shape of space and time itself. We will sit inside a falling room and feel our weight simply vanish, and we will watch a station fall around the earth without ever landing. If someone in your life lies awake with a restless mind, this slow journey can be a quiet harbor for them, a gentle voice to keep them company until sleep arrives. So let the day loosen its hold now, and let your breathing settle into a slower rhythm. There is nothing here to solve, and no place you must reach. You will only rest, while the shape of the universe is explained to you in a hush. Let us begin. Begin with the simplest thing you know about your own body, the feeling of being heavy. You are sitting or lying down as you listen, and there is a steady pressure where you meet the world, the chair against your back, the mattress under your shoulders, the floor beneath your feet. That pressure feels like gravity. It feels like the very sensation of being pulled toward the center of the earth. And yet, in a way that is easy to miss, that is not what you are feeling at all. Consider what is really touching you. The floor cannot pull. A chair has no way to reach into your body. All either of them can do is push. When you stand, the ground pushes up through the soles of your feet, with exactly the firmness needed to stop you sinking. And when you lie down, the bed pushes up along the whole length of you. The feeling you have named heaviness is the feeling of being pushed gently and constantly upward. It is the ground holding you back from a fall you would otherwise be taking. A bathroom scale makes this quietly clear. You think it measures how hard gravity tugs on you, but a scale has no way to sense a tug. All it can measure is how hard you press down on its surface, which is the same as how hard it presses back up on you. It reads the push between your body and the world. Stand on a scale in a lift that begins to rise quickly, and the number climbs, because the floor is pressing harder. Let the lift drop away beneath you, and the number falls toward nothing, because the floor has stopped pressing at all. There is a small version of this that your body already knows well. Bring to mind the first moment a lift begins to drop. That light, hollow feeling low in the belly, the brief sense that you have grown a little lighter. In that instant, the floor beneath your feet has started to fall away, and it presses against you with slightly less firmness. And your body reports the change at once as a loss of weight. A gentle dip in the road does the same thing in a car, and a swing does it at the top of its arc. Each of these is the same quiet lesson told again, that the feeling of weight lives entirely in the push of a surface and softens the moment the push begins to ease. Now imagine that the floor could fall away completely, all at once, and keep falling. The push would vanish, and with it every trace of your weight. This is exactly what a diver feels in the moment after leaving the board, and what a person feels at the crest of a tall fairground ride, that swooping lightness as the seat drops away beneath them. For those brief seconds they are in true free fall, with nothing pressing up on them at all. and their weight is simply gone. The sensation people chase on such rides, that thrilling floating hollowness, is nothing more than the honest feeling of a body with no surface pushing against it. Here is a gentle way to picture it. Imagine a hand cupped open beneath a small stone, holding it up against its fall. The stone rests in the palm, and if the stone could feel, all it would ever notice is the palm, the firm, cool surface pressing into it from below. It would never feel the fall itself. Its whole sensation of weight would be the hand refusing to let it drop. You are that stone, and the ground is that hand. And every ounce of heaviness you have ever felt has been the surface of the world pressing up to hold you. So what happens when the hand opens? When there is nothing pressing up on you at all, the entire feeling you call weight simply goes away. Not lessens, but vanishes. This is the quiet doorway we will walk through tonight, because it tells us something surprising about the pull we thought we understood. If the feeling of gravity is really the feeling of the ground, then gravity itself, the thing that draws you downward, is something you have never once felt in your life. From here, we drift toward the man who first understood why. More than 100 years ago, a young clerk in a patent office in Switzerland sat thinking about falling, and had what he would later call the happiest thought of his life. The year was 1907. Albert Einstein pictured a person falling freely, with nothing to stop them, and realized something plain and beautiful. A person in free fall does not feel their own weight. If they let go of anything in their hand, it would fall beside them at exactly the same rate, and so it would seem to hover there, motionless, right next to them. Inside their falling world, gravity would appear to have switched off. Picture a small room, sealed, with no windows, drifting in the middle of a long fall toward a planet far below. You are inside it. Push off gently from one wall and float across to the other. You take a cup from your pocket and let it go, and it stays exactly where you left it, hanging in the air beside your shoulder. Pour water from a bottle and it does not stream downward. It gathers into a slow, trembling globe. Everything inside this falling room behaves as though there were no gravity anywhere near, and there is no test you could run, sealed inside, to prove that you are falling at all. This was the seed of the happiest thought. Take that same sealed room and set it out in the deep between the stars, far from any world, truly beyond the reach of any nearby pull. Inside, everything floats. Now bring the falling room back beside its planet. Inside, everything also floats. The two situations feel completely identical from within. Free fall toward a world and quiet drifting in empty space produce the very same experience. If the inside of a falling room is indistinguishable from the inside of a room where no gravity acts, then falling and floating are, in some deep sense, the same state. It is worth pausing on how humble the beginning of this idea was. Einstein was not standing at a great instrument or peering through a telescope when it came to him. He was sitting at an ordinary desk, doing ordinary work, letting his mind wander over a simple picture of a person falling from a rooftop. What he noticed was only that such a person would not feel their own weight while they fell, and that this small plain fact might mean something enormous. The whole of his new understanding of gravity grew from that single quiet noticing, turned over patiently for years. Some of the deepest truths about the universe have entered the world through the smallest and gentlest of doorways. The power of the falling room is that it takes away every excuse the older idea had. If gravity were truly a special force reaching out from a planet, then it ought to feel like something, ought to leave some trace that a careful experiment could catch. Even inside a falling room, yet it leaves no trace at all. Seal yourself inside, let the room fall freely, and every measurement you could make would tell you that no gravity was present anywhere near. The force we imagined simply refuses to show itself. And a force that vanishes so completely, the moment you stop resisting it, begins to look less like a force and more like the shape of the path you were always free to take. Einstein turned this small insight over for 8 patient years, and it grew into a new picture of the whole universe. He called the finished idea general relativity, and he completed it in 1915. Its starting point is exactly the falling room. If a person in free fall feels no gravity, then free fall must be the most natural state there is, the state of an object left completely alone, with nothing pushing or pulling on it. Sitting still in a chair, pressed by the floor, is the unusual state. The chair is the thing interfering. Its fall is the thing that is free. Sit with how upside down this is from the way we usually speak. We say a falling object is being acted upon, and a resting object is at peace. Einstein saw it the other way. The falling apple, the drifting astronaut, the plunging elevator. These are the things left alone, following their natural course through the world. But the book resting on the table is the one being constantly interfered with, shoved upward by the table, again and again, kept from the free path it would rather take. From here, we drift toward what that free path actually feels like, when a body is truly let go. Long before anyone flew to orbit, people found ways to taste this feeling of nothing on the ground. In a few places around the world, engineers built tall towers with a long empty shaft running down the middle, and inside that shaft they let sealed capsules drop. For a handful of seconds, everything within the capsule is in perfect free fall. A small experiment placed inside floats as though it had been carried into deep space. Flames burn into soft round balls instead of pointed tongues. Drops of liquid pull themselves into slow spheres. For those few seconds, in a tower a few hundred feet tall, gravity seems to leave the room. There is a gentler and longer way to feel it in an aircraft that flies a long smooth arc through the sky. The plane climbs steeply, then eases over the top of its curve and follows the exact path a thrown stone would take if you tossed it high into the air. During that graceful arc, the plane and everyone inside it are all falling together along the same curve, and because they fall together, the people float. They drift up from the floor and hang in the cabin, turning slowly, laughing in the quiet. The plane is not beyond gravity, it is simply falling and carrying its passengers down along with it, so that nothing presses on anyone at all. Those long, smooth arcs are how many of the people who fly to orbit first learn what falling feels like. Aboard such flights, everything that is not tied down rises gently from the floor. Water pours into slow trembling globes, and a person can turn weightless somersaults in the middle of the cabin. Each arc lasts less than half a minute before the plane must pull up and climb again to begin the next. And in that brief window, the whole cabin becomes a falling room, exactly like the one Einstein imagined. It is a gentle gift to be able to gather a few seconds of the feeling of deep space by flying a careful curve through the ordinary sky. On the ground, the towers do the same in miniature, and they are quietly beautiful to picture. Within a falling capsule, a candle flame no longer rises to a point, because there is no cooler air sinking beneath it to push the hot air upward. The flame simply glows outward into a soft round ball, calm and blue at its edges. Small living things, seedlings and cells, ride these brief falls so that patient people can watch how growth itself behaves when weight is taken away. Each of these little experiments is a way of visiting deep space for a handful of seconds without ever leaving the Earth, by letting a sealed room do nothing at all but fall. This is the true meaning of the word weightlessness, and it is one of the most quietly misunderstood words we have. When you see people floating inside a spacecraft, drifting past the windows with slow ease, it is natural to think they have traveled somewhere that gravity cannot reach. They have not. At the height where they orbit, the Earth still pulls on them, almost as strongly as it pulls on you in your bed tonight. They float for one reason only. All of them, they and their spacecraft and every loose object around them, are falling together at the same rate along the same path. When everything falls together, nothing has anything to press against, and so nothing has any weight. Think of what your body is really telling you when it feels heavy or light. It is not measuring gravity. What it measures is the difference between your fall and the fall of whatever is beneath you. On the ground, the floor is held still, refusing to fall while your body wants to. That disagreement is what you feel as weight. In the falling plane, the floor is falling at the same rate you are, so there is no disagreement and no feeling. The sensation of weight is not the pull of the Earth. It is the argument between you and the surface that will not let you follow it. Notice how this quietly settles a small confusion that trips almost everyone. People often speak of astronauts as having escaped gravity, or of deep space as a place with no gravity in it. Both ways of speaking miss the truth by a wide margin. Gravity reaches everywhere, gentle and unbroken, filling the whole of space with its soft slopes and valleys, and there is nowhere you could ever travel to leave it entirely behind. What the astronaut has found is not an escape from gravity, but a way of surrendering to it so completely, falling so freely, that its usual companion, the pressing surface, is simply no longer there. And so when we say the astronaut is weightless, we do not mean gravity has gone. We mean only that nothing is pressing back. Weight was always the pressing, never the gravity, and so weight can vanish, while gravity remains full and steady all around. This small correction is worth carrying gently with you, because it turns a place that sounds empty and cold into something warmer and truer, a universe filled everywhere with the same soft shape that holds you now, a shape you can rest within whether a surface presses on you or not. So the feeling of nothing turns out to be the most honest feeling of all. It is what a body feels when it is finally left alone, moving exactly as the universe invites it to move, with nothing interrupting the journey. Everything we usually call the pull of gravity is really the story of surfaces refusing that invitation, tables and floors and the solid crust of the Earth all pushing back, all keeping us from the free path. From here, we drift toward the shape of that path and the surprising claim that it is, in its own way, perfectly straight. Here is a question that sounds almost too simple to ask. When a ball rolls down into a valley, Why does it go? The everyday answer is that gravity pulls it toward the bottom. But watch the ball closely, and something subtler is true. The ball is not being yanked. It is simply rolling forward, following the ground beneath it, and the ground happens to slope downward. The ball takes the most natural path available to it, and that path leads into the low place. It did not choose the valley. The valley was already there, in the shape of the land, and the ball only followed the shape. Einstein's great idea was that gravity works like the shape of that land. But the land is not the ground. It is space and time themselves. Every object left free, with nothing pushing on it, moves along the straightest path it possibly can. In empty space, far from everything, that straight path is what you would expect, a simple line carried onward and onward. But near a heavy object, space and time are gently curved, like the sloping sides of the valley, and the straightest possible path through that curved region bends. A falling apple is not being pulled toward the earth. It is coasting along the straightest line available, and that line happens to lead to the ground. We have a name for the straightest possible path through curved space and time. It is called a geodesic, and it is one of the loveliest ideas in all of physics. On the flat page of a map, the straightest path between 2 points is an ordinary line. But on the curved surface of the Earth, the straightest path a plane can fly is a gentle arc that looks bent on the map, but is truly as direct as the round world allows. A geodesic is that same idea carried into the deeper fabric of space and time. Objects in free fall are not wandering, and they are not being tugged. They are traveling as straight as the shape of the universe permits. The idea of a straight path that looks bent is worth sitting with, because it lives all around us. Think of two cities far apart on the round Earth, and the path a plane flies between them. On a flat map, the route often looks like a great curving arc, bowing far to the north, and it seems the plane is wandering off the direct line. Yet, that arc is the most direct path there is across the curved surface of the globe, shorter than the straight line drawn on the flat map. The line only looks bent because we have tried to flatten a round world onto a page. In truth, the plane is flying as straight as the Earth allows, and its straightness curves because the world beneath it curves. A geodesic is that same idea, carried from the curved surface of the Earth into the curved depths of space and time. When a comet swings in from the far dark, loops close around the Sunday, and sails back out again, it is not being whipped around a corner by a great force. It is coasting freely along the straightest path available to it, through the curved space near the Sunday, a path that happens to bend into a long, graceful arc. From far away, that arc looks like the work of a mighty pull. Yet from the comet's own point of view, nothing pulls at all. It is drifting in the straightest line it can, and only the shape of space has bent that line into a curve. This is why the older word, force, begins to feel out of place. A force, in the usual sense, is a push or a pull that shoves an object off the path it was taking. When you kick a ball, you apply a force, and the ball leaps away from its resting place. But nothing kicks the falling apple, nothing shoves the orbiting station. They are already on the straightest path, and they simply keep to it. What we called the force of gravity is really the curve of the path itself, quietly guiding everything that travels along it without ever needing to push. And this reveals the gentle sleight of the whole thing. We feel a pull, because our path wants to bend toward the earth, and the ground stands in the way, pressing up to stop us from following it. The pull we imagine reaching up out of the planet is really the shape of space and time, inviting us along a curve, while the floor holds us off that curve and calls the holding a weight. From here, we drift toward the thing that does the curving and ask how a planet could bend something as vast and empty as space. To picture what curved space and time might mean, begin with the idea of a perfectly even emptiness. Imagine all of space, threaded with a faint grid, an endless lattice of cool lines, reaching in every direction, evenly spaced, with nothing to disturb them. In a region far from any star or planet, this lattice stays flat and true. An object drifting through it travels in a plain, straight line, crossing the squares one after another at a steady pace, going on forever without turning. This is space with no gravity in it, calm and unbent, the blank page before anything is written. Now set a world into that emptiness. According to general relativity, matter and energy tell space and time how to curve. And the more matter you gather in one place, the deeper the curve becomes. Around the Earth, the even lattice sags into a smooth, wide well, the lines stretching and bending as they draw near the planet. Nothing has been pushed. The shape of space itself has simply changed in the presence of the world, and every object that passes through this region now travels through curved lines instead of straight ones, and so its natural path bends inward toward the low center of the well. This is the whole heart of the idea, and it can be said in a single quiet sentence. Matter tells space and time how to curve, and the curve of space and time tells matter how to move. The Earth does not reach out and grab the falling stone. Instead, it shapes the space around itself into a gentle valley, and the stone, following the straightest path it can, rolls down the inner slope of that valley. What we experience as the pull of the planet is the slope of the space we are standing in. A slope we cannot see, felt only when the ground stops us from sliding down it. It is important to hold on to one word in all of this, because it changes everything. The Earth does not only curve space, it curves space and time together as a single joined fabric. And the time part matters even more than the space part for the falling we know. When you drop a stone, almost all of the bending that guides it comes from the way the Earth curves time, not simply the way it curves space. The stone, following the straightest path through curved space and time, is really being guided by the fact that time itself flows a touch slower nearer the ground. We will return to that slowing of time later, but plant it here, gently as part of the shape. There is a small caution worth adding, so the picture stays true. When people first meet this idea, they often imagine a heavy ball resting on a stretched sheet, dimpling it downward, with smaller balls rolling in toward it. That picture is a helpful first step, but it quietly cheats, because it uses ordinary gravity pulling the balls down into the sheet to explain gravity itself. The real curving is not a dimple in a flat rubber sheet hanging in some room. It is a bending of space and time themselves, in every direction at once, with no floor beneath it and no up or down outside it. Let the sheet go and keep only the truth it was pointing at, that matter bends the very fabric that everything else must move through. Every object with mass makes its own gentle well in the fabric of space and time, and the wells nest one inside another across the whole universe. A moon makes a small shallow dimple. Around a planet, the dip is broader and deeper. A star carves a wide sweeping valley, and the planets circle within it, like marbles rolling around the inside of a great smooth bowl, never falling to the center because they are always moving sideways as they fall. The night sky, seen this way, is not a scatter of lights on a flat ceiling. It is a vast, rolling landscape of unseen valleys, each carved by the weight of what sits at its heart. There is something restful in seeing it this way. The heaviness that holds you to your bed is not a chain reaching up from the core of the planet. It is the gentle shape of the space you are lying in, a shallow valley carved by the whole mass of the earth, and you are simply resting near its bottom, held by the floor from rolling any deeper. Nothing is straining, nor is anything pulling. The world has bent the space around itself, and you have come to rest in the curve. From here, we drift back to an ordinary apple and ask why two very different pictures of its fall both turn out to work. There is an old story about an apple, and it is worth telling gently because it holds two truths at once. More than 300 years ago, Isaac Newton watched an apple come down from a tree and began to wonder whether the same influence that brought the apple to the ground might reach all the way to the moon. From that wondering, he built a magnificent description of gravity, one that treated it as a genuine force, an invisible pull reaching across space between every object and every other. Newton's picture was so accurate that we used it to send travelers to the moon and probes to the far planets, and we use it still. So here we have two very different stories about one falling apple. In Newton's story, the Earth reaches out and pulls the apple down with a force, and the apple, feeling that pull, accelerates toward the ground. But in Einstein's story, no force touches the apple at all. The apple simply follows the straightest path through the curved space around the Earth, coasting freely while the ground rushes up to meet it. Two stories, one apple, and both of them predict the very same fall, the same speed, the same soft landing in the grass. For almost everything in daily life, the two pictures agree so closely that you could never tell them apart. Why keep the deeper story then, if the older one works so well? Because when you look at the extremes, the two stories quietly part ways, and only Einstein's holds true. Near very heavy objects, where space is curved sharply, Newton's numbers begin to drift a little from what we actually observe. The planet Mercury, swinging close to the Sunday, traces a path that Newton's force cannot fully explain, but that the curving of space predicts exactly. In the strongest fields, where matter is packed tightest, only the picture of curved space and time keeps step with the universe. Newton was not wrong. He was beautifully, usefully incomplete. Consider the small puzzle of Mercury, for it is a lovely example of how a tiny disagreement can open a door. Mercury is the innermost planet, swinging closest to the Sunday, deepest into the great valley the Sunday carves in space. For a long while, careful watchers noticed that the long oval of its orbit does not stay quite still. It slowly turns, so that over many years the whole oval sweeps gently around the Sunday, tracing a slow pattern like the petals of a rose. Newton's force explained almost all of that turning by counting the gentle tugs of the other planets, almost all, but not quite. A tiny part of the turning was left over, unexplained, a small stubborn remainder that would not fit. That tiny leftover was one of the first triumphs of the deeper idea. When Einstein worked out how Mercury would move through the curved space near the Sunday, out came exactly the missing piece of turning, the small remainder that Newton's force could not supply. Nothing had to be added by hand, and no new force invented. The extra drift simply fell out of the shape of space itself, in precisely the amount observed. It was a quiet moment, a small planet's slow wander matching a new picture of the cosmos to the last measure, and it was one of the first signs that the shape of space was not a fancy but a fact. So we carry both pictures forward without any quarrel between them. For the falling of a spoon, the flight of a ball, the arc of a thrown stone, Newton's simpler idea of a pull is a fine and faithful guide, easy to use and true to the last hair. Yet, for the deepest wells and the swiftest motions, and for the exact turning of Mercury, only the curving of space and time will do. One is the everyday shorthand, close enough for the kitchen and the launch pad. The other is the deeper account, true everywhere, from the falling apple to the farthest reaches of the sky. Both agree that the apple comes down, yet only the deeper one tells us why, without any pull at all. It helps to remember how gentle the Earth's curve of space really is. Our planet, for all its mass, bends space and time only slightly, and Newton's simpler force is an excellent shortcut across that gentle bending. It is a little like describing the surface of a calm lake as perfectly flat. For rowing across it, flat is a fine and true enough description. Only when you sail far enough to watch a distant shore sink below the horizon do you need the deeper truth that the water curves with the round earth beneath it. Newton's gravity is the flat lake description. Einstein's is the round world underneath. This is why we can hold both pictures at once without any conflict. When you drop a spoon in your kitchen, you may happily think of it as pulled toward the floor, and no harm is done. For the two descriptions agree to a hair, but the true account, the one that holds everywhere, from the falling spoon to the swing of Mercury to the strongest depths of the cosmos, is the quieter one. There is no pull anywhere, only shape and things quietly following it. From here, we drift up to a place where following that shape becomes a kind of endless gentle falling that never reaches the ground. Some 250 miles above your head, a bright structure the size of a large house sweeps around the Earth, over and over, once every 90 minutes or so. Inside it, people float. They sleep tethered, so they do not drift into the walls. They watch water gather into slow globes. They push off gently and glide the length of a room. It is easy to imagine they have escaped gravity, that they have risen to a height where the Earth finally lets go. But the Earth has not let go at all. At the height where the station orbits, the planet still pulls on it nearly as strongly as it pulls on the ground. There is a beautiful thought experiment, first imagined by Newton himself, that makes the whole thing clear. Picture a cannon set on an impossibly tall mountain, above the air, firing a ball out sideways. Fire it gently, and the ball arcs out and comes down to the ground, a short way off. Give it more force, and it arcs farther before it lands. Send it out hard enough, and something wonderful happens. The ball falls toward the Earth, exactly as fast as the round Earth curves away beneath it, so that it keeps missing the ground, coming down and down forever, while the horizon keeps dropping out from under it. that endless falling that never arrives, is an orbit. This is the quiet secret of everything that circles our world. The space station is not held up there by any engine, and it is not resting on anything. It is falling constantly, the same way the apple falls, following the straightest path through the curved space around the planet. The only difference is that it is also moving sideways at tremendous speed, roughly 5 miles every second, so that its fall carries it around the curve of the Earth, instead of down onto it. It is forever tipping over the edge of the horizon and forever missing, tracing a great circle in the sky. The astronauts float because they are falling, and their station is falling with them. Rest for a moment on the pace of that endless fall, for it is faster than almost anything in our experience. The station circles the whole Earth in about 90 minutes, which means that for the people aboard, the sun rises and sets roughly every hour and a half. In a single ordinary day on the ground, they watch some 16 sunrises and as many soft blue sunsets, the horizon lighting and dimming again and again beneath them as they fall around the world. They are moving at something near 5 miles in every second, quick enough to cross a whole country in a few minutes, and yet inside their falling home everything is perfectly calm, and a pen left in the air simply hangs there, going nowhere at all. It bears repeating gently because it is so easy to forget. The station is not floating in some region beyond gravity's reach. At the height where it orbits, only a couple of 100 miles up, the pull of the Earth is still very nearly as strong as it is at the surface, dimmed by only a small fraction. If you could somehow build a tower that tall and stand still at the top of it, you would feel almost your full weight, the tower pressing up on your feet just as the ground does now. The astronauts float, not because gravity has faded, but because they and their home are falling together. And falling together is what weightlessness has always meant. And what is true of the station is true of every quiet companion that circles our world. The satellites that carry our messages and watch our weather are all falling, each one running sideways just fast enough to keep missing the ground, each one tracing its own patient ring, higher and slower and grander than all of them. The moon does exactly the same, falling toward us forever and forever sailing past. To look up at any of them is to watch the same endless, effortless motion, a fall with no bottom, held in the curve of space. None of it is being held up. All of it is simply falling and missing in perfect calm. Feel how this ties back to the falling room from the beginning of our journey. The astronauts are simply living inside that sealed falling room. Only their room happens to be moving so fast sideways that it never reaches the bottom of its fall. Everything within it falls together: the walls, the air, the people, the floating pen, and so nothing presses on anything, and weight disappears. They are not beyond gravity. In truth, they are as deep inside it as we are. They have only found a way to fall so gracefully and so sideways that the ground never rises to stop them, and the free path becomes a ring around the world. There is a gentle beauty in this that is worth resting on as you drift. Everything in orbit, every station, every satellite, the moon itself, is engaged in the same slow, endless act of falling and missing. The moon has been falling toward the Earth for longer than there have been oceans, and it keeps missing, sailing on around us in a great patient circle. Nothing up there is holding still, nor is anything up there being held. It is all coasting along the curved shape of space, forever falling toward a center. it will never reach. From here, we drift back down to the ground and sit inside two rooms that cannot tell themselves apart. Return now to a sealed room with no windows, and imagine you wake inside it with no memory of how you came to be there. You feel your normal weight. Your feet press the floor, a dropped cup falls to the ground. Everything seems entirely ordinary. Now here is the question at the center of Einstein's whole idea. From inside, sealed away, can you tell whether your room is resting on the surface of a planet, held by its gravity, or whether it is far out in empty space, being pulled steadily forward by some great engine, so that the floor rises to meet your feet? The answer, remarkably, is that you cannot tell at all. Drop the cup in the room on the planet, and it falls to the floor, because the space around the planet is curved, and the cup follows that curve. Now drop the same cup in the room being pushed through empty space, and it also falls to the floor, but for a different reason, because the floor is accelerating upward to meet the cup while the cup drifts freely. From the inside, the two falls look exactly the same. The cup lands the same way, at the same rate, with the same soft sound. No experiment you could perform, sealed in that room, would reveal which situation you were in. Gravity and steady acceleration produce identical worlds. Einstein pressed on this equivalence until it gave up a startling gift. Picture a thin beam of light crossing your accelerating room, entering through a tiny hole in one wall and traveling to the far wall. While the light crosses, the room is rushing upward, so by the time the beam reaches the far side, the wall has risen a little and the light strikes lower than where it came in. From inside, it looks as though the beam of light has bent gently downward as it crossed the room. And if a sealed room being accelerated bends light, then a sealed room sitting in gravity must bend it too, for the two are indistinguishable. Gravity, Einstein realized, must bend light itself. This is the moment the whole picture locks together. If gravity is truly the curving of space and time, then everything that travels through that region must follow the curve. Not only apples and cups and space stations, but light as well. Light always takes the straightest possible path available to it. In flat, empty space, that path is a plain, straight line. But near a heavy object, where space itself is bent, the straightest path bends with it, and so a ray of starlight passing close to a massive body is gently deflected, curving around it like a stream bending around a stone. The bending of light was a prediction no one had ever imagined testing. Let us make the equivalence of the two rooms as plain as we can, because everything hangs from it. In the first room, resting on a planet, you feel your weight and a dropped ball falls to the floor, all because the space around the planet is curved and the ball follows that curve. And in the second room, out in the empty dark, a great engine pushes it steadily forward, so the floor rushes up to meet a ball that is simply drifting freely. From outside, the two situations could not look more different. One sitting still on a world, one racing through the void. Yet from inside, sealed away with no window, they are the same in every way you could ever measure. This is the heart of what Einstein called the principle of equivalence, and its plainness is its power. If gravity and steady acceleration produce exactly the same experience, with no test able to tell them apart, then in a deep sense, they must be the same kind of thing. Whatever is true of one must be true of the other. And this simple rule becomes a key that unlocks door after door. because it lets us take anything we understand about a room being pushed through empty space, where there is no mysterious gravity at all, and carry it straight over into a room sitting in a gravitational field. Whatever happens in the accelerating room must also happen in gravity. So follow that key to the beam of light one more time. Slowly, in the room pushed through empty space, the light crosses from one wall to the other, while the room rushes upward, and so it lands a little lower than it entered and appears to bend downward. Because the room in gravity is identical in every measurable way, light must bend downward there too. Nothing pushes on the light. It has no weight to feel a pull. Instead, it takes the straightest path it can. And in a room where space and time are curved, that path is a gentle curve. From the equivalence of two sealed rooms, the whole universe of curved light unfolds. And this is why the equivalence of the two rooms matters so much. It was not a curiosity. Rather, it was the thread that once pulled, unraveled the old idea of gravity as a simple pull and revealed the deeper shape beneath. Because falling and floating are the same, because gravity and acceleration are the same, light must bend, time must shift, and the universe must be curved. Einstein followed that single thread, the happiest thought about a falling person, all the way to a new understanding of space, time, and light together. From here, we drift toward the most surprising gift of that curved space, the way it quietly changes the flow of time itself. We tend to think of time as a single steady river, flowing at the same rate for everyone and everything, everywhere at once. General relativity gently overturns even this. Because gravity is the curving of space and time together, and because deeper in a gravitational well, the curving is stronger, time itself flows a little more slowly the lower you go. A clock resting on the floor runs very slightly behind a clock resting on a high shelf in the same room. The difference is unimaginably small over such a short distance, far too tiny to feel, and yet it is real, and it has been measured. Sit with how quietly astonishing this is. Your head right now is aging a hair faster than your feet, because your head sits a little higher out of the Earth's well than your feet do, where time runs a touch quicker. Over a whole human lifetime, the gap adds up to less than the blink of an eye, so small that no sense could catch it. But scientists have taken two exquisitely precise clocks, set one just a foot or so above the other, and watched the higher one tick ahead of the lower one by exactly the amount the curving of time predicts. The shelf and the floor really do live in slightly different flows of time. People have carried this slowing of time up into the sky to check it directly, and the result is quietly marvelous. Precise clocks were placed aboard planes and flown high above the ground for many hours, while identical clocks were kept below, and when the travelers returned, their clocks and the ground clocks no longer agreed by just the tiny amount the shape of time predicted. Time really had flowed a touch faster up where the curve of space is gentler. It is a difference measured in billionths of a second, far too small for any sense to feel, and yet it is as real as the ground beneath you, woven into the height of every shelf and every hill. The gentlest way to feel the idea is to bring it home to your own body. As you lie there, your head rests a little higher out of the Earth's valley in space than your feet do, in a place where time runs the tiniest bit quicker. So your head is aging just barely faster than your feet and has been all your life. The gap is so small that over a whole lifetime, It adds up to a fraction of a single second, far less than a heartbeat, utterly beyond noticing. And yet, it is truly there. Even within the small space of a resting body, the shape of the world lays down two faintly different rivers of time, one at the head and one at the feet. The rule is simple and calm. Sink deeper into the well, where space and time are most sharply curved, and the slower your clock runs compared to clocks higher up, at the bottom of the well, near the surface of a heavy world, time is at its slowest. Far out, where the well flattens toward the emptiness between the stars, time flows quickest of all. This is not an illusion of moving clocks or a trick of measurement. It is the shape of time itself, sloping along with space, so that the very rate at which seconds pass depends on how deep in the curve you happen to be standing. There is something tender in this idea when you let it settle. Everyone who has ever lived close to the ground, in the low places of the world, has lived in time that runs a whisker slower than the time on a mountaintop. A person by the sea and a person on a high plateau are, in the most literal sense, moving through time at faintly different speeds, and the difference, though far too small to notice, is woven into the shape of the planet beneath them. Time is not a fixed backdrop. It bends and pools with the landscape of space, running slow in the deep valleys and quick on the high ground. For most of history, this would have remained a beautiful curiosity, a thing true in principle, but far too subtle to matter to anyone's day. And that is exactly what makes the next part of our journey so quietly remarkable. This faint slowing of time, this bending of the seconds by the shape of space, is not only real, it is something we now depend on quietly, every single day in a small machine that many of us carry in a pocket. From here, we drift upward to a ring of clocks circling the Earth, and to the reason they must be told a gentle lie about time. High above the Earth, far higher than the space station, a fleet of satellites circles the planet, and inside each one rides a clock of extraordinary precision. These are the satellites that let a phone or a car know exactly where it is on the surface of the world. The way they do it is beautifully simple in principle. Each satellite broadcasts the time, again and again, with great accuracy. Your device listens to several of them at once, compares how long each signal took to arrive, and from those tiny differences works out its own position. The whole system rests entirely on the satellites and your device agreeing exactly on what time it is. Now recall what we have just learned about time, and a quiet problem appears. The satellites sit high up, far out of the Earth's gravitational well, where the curving of space and time is gentler and time runs quicker, so their clocks, up in that shallower curve, tick faster than the clocks down on the ground. At the same time, the satellites are racing around the Earth at great speed, and rapid motion, by a separate effect, makes a moving clock run slightly slow. Two influences then, pulling in opposite directions. The height speeds the clocks up, and the speed slows them down, and the two do not cancel. When you add the two effects together, the height wins. The clocks aboard the navigation satellites, high in their shallow curve of space and time, run faster than clocks on the ground by about 38 millionths of a second every single day. That is an almost absurdly tiny amount, a number so small it seems it could never matter to anything. And yet, for a system that finds your position by comparing the timing of signals down to billionths of a second, 38 millionths of a second a day is an enormous and growing error. Left uncorrected, it would ruin everything the system is meant to do. To feel why so tiny a slippage matters, remember how the whole system finds you. The signals from the satellites travel at the speed of light, which crosses about a foot in a single billionth of a second. Your device works out where you are by measuring the timing of those signals, that finally down to billionths of a second, and turning each tiny delay into a distance. So if a satellite's clock runs even a little ahead of true, every distance it hands you comes out a little wrong, and your place on the map shifts. A slip of billionths of a second in the clock becomes feet of error on the ground, and a slip that grows all day becomes an error that grows all day with it. So watch what would happen across a single day if no one corrected for the curve of time. At the first light of morning, with the clocks freshly matched, your position would be very nearly right, off by only a step or two. But as the hours passed and the high clocks pulled steadily ahead, that small error would swell, drifting wider and wider, until by the following morning, the map would place you miles from where you truly stood. The whole graceful system would unravel within hours, all for want of accounting for the fact that time runs a little quicker high above the ground than it does at your feet. Imagine what would happen if the engineers simply ignored it. On the first morning, your position would be off by only a few feet, hardly worth noticing. But the error would not hold still. It would grow, hour after hour, as the satellite clocks pulled steadily ahead of the ground, and within a single day, the location the system reported would drift off by several miles. A map that placed you miles from where you truly stood would be worse than no map at all. The whole delicate art of finding your way by the clocks in the sky would collapse within hours, all because of the gentle bending of time by the shape of space. So the engineers do something quietly profound. Before each satellite is sent up, its clock is deliberately set to run a touch slow, tuned so that once it reaches its high, fast orbit, the curving of time will speed it up to exactly match the clocks on the ground. They build Einstein's idea directly into the hardware, correcting for the slope of time before the satellite ever leaves the launch pad. Every time a phone shows you where you are, it is quietly relying on the fact that time runs differently up in the sky than down at your feet. The bending of time is not a distant abstraction. It is the reason you can find your way home. From here, we drift outward again to watch the same curving of space reach out and bend the light of distant stars. When Einstein finished his idea, it made a bold and testable promise. If gravity truly is the curving of space, then starlight passing close to a heavy object should be bent, its path deflected as it follows the curve. The trouble was finding a way to see it. Our nearest object, massive enough to bend light noticeably, is the Sunday. But the Sunday is so blindingly bright that no one could ever see a faint star sitting just beside it in the sky. There was only one moment when the thing might be caught, when the moon slides in front of the Sunday and turns day briefly to a deep, cool twilight. In 1919, astronomers traveled to watch a total eclipse for exactly this reason. With the Sunday's glare blocked by the moon, the stars that lie just beyond its edge became visible, and the astronomers measured their positions with great care. If Einstein was right, the light of those stars, grazing past the Sunday on its way to us, would be bent by the curved space around it, and the stars would appear to have shifted very slightly from their true places. the measurements came back, and the stars had moved by just the amount the curving of space predicted. And so the bending of light was real, and the world took notice. Picture for a moment what those watchers actually did, for there is a quiet drama in it. They carried delicate instruments to remote corners of the world, set them up under open skies, and waited for the few short minutes when the moon would slide fully across the Sunday. When that shadow fell and the day dimmed to a deep twilight, the stars nearest the Sunday blinked into view, and the watchers hurried to record their exact places before the light returned. Then they compared those places with where the same stars sat in the ordinary night, months apart from the Sunday. The small shift between the two told them that the Sunday's curved space had nudged the starlight aside, exactly as a young clerk had foreseen years before. That single eclipse changed how the world thought about gravity, gently and for good. Until then, most people had lived their whole lives inside Newton's picture of an invisible pull, and it had served beautifully for more than 2 centuries. Now the stars themselves had shifted in the sky to confirm a stranger and deeper account. That space is curved, and light must follow its curve. The idea reached far beyond the world of astronomers, and the young clerk who had dreamed it became known across the whole world almost overnight. And ever since, in 100 quieter ways, careful measurements have kept confirming it. The deflection of radio waves grazing the Sunday, the slow bending of signals from distant probes, each one agreeing with the shape of space to finer and finer measure. Today, this bending of light has become one of astronomy's most beautiful tools. When the light of a very distant galaxy passes a massive cluster of galaxies on its long journey toward us, the curved space around that cluster bends the light like a grate. In perfect lens, the distant galaxy appears stretched into graceful arcs, sometimes smeared into a glowing ring, sometimes multiplied into several images of the same faint object. We call this gravitational lensing, and it lets us see galaxies so far away that their light would otherwise be far too faint to gather. The curve of space becomes a lens, magnifying the deep past. There is a quiet lesson folded into this. Light, which seems the freest and most weightless thing in the universe, must also obey the shape of space. It does not feel a pull, for it has no weight to pull upon. Instead, it simply travels the straightest path available. And where space is curved, the straightest path curves too. A ray of light leaving a distant galaxy is like a thread laid down across the rolling landscape of space, following every gentle valley and rise along the way, arriving at last a little bent, a little redirected, carrying in its very path a record of every mass it passed. Even light must go the way the shape allows. And so the same idea we began with, back in the falling room, reaches all the way to the edge of the visible universe. The apple, the space station, the clock, the beam of starlight, all of them follow the same simple rule. Nothing is pulled. Everything travels the straightest path it can through a space that is gently curved by all the matter within it. The whole grand machinery of gravity, from the weight of your own body against the bed to the bending of ancient light around a cluster of galaxies, is one calm idea, worn smooth and told over and over. From here, we drift toward the one place where the shape of space reaches down into the sea itself and slowly lifts the tides. Twice a day, along every coast on Earth, the sea rises slowly up the sand and then slips slowly back again. We call it the tide, and it is one of the oldest rhythms people have watched. For a long time, the tides seemed to be a simple matter of the moon pulling the water toward itself. But the curving of space gives us a truer and gentler picture, and it explains something the simple pull cannot. Why there are two swells of high water at once, one on the side of the Earth facing the moon, and one on the side facing directly away. The reason is that the moon does not curve the space around the Earth by the same amount everywhere. On the near side, the Earth sits a little closer to the moon, in a slightly steeper part of the curve, while the far side lies a little farther away, in a gentler part. So the near ocean falls toward the moon a touch more eagerly than the solid center of the Earth does, and it draws ahead, swelling outward, and the far ocean falls toward the moon a touch less eagerly than the center does. So the Earth slips forward and leaves that water behind, swelling outward on the opposite side. Two bulges, born from the difference in the curve across the width of the world. As the Earth turns through a day, each stretch of coast is carried through both of these swells in turn. And so most shores see the water rise and fall roughly twice between one sunrise and the next. The tide is not the moon reaching down and lifting the sea. It is the sea responding to the fact that the shape of space is slightly steeper on one side of the Earth than the other. This is a difference so gentle that it moves the ocean only by a matter of feet, and yet it has set the rhythm of harbors and shorelines for as long as there has been water on the world. It is worth noticing that the Sunday plays its own gentler part in this slow rhythm. The Sunday is enormously more massive than the moon, but it lies so very far away that the difference in its curve across the width of the Earth is smaller than the moon's, and so its tides are the quieter of the two. When the Sunday and the moon line up, their two pulls on the difference add together, and the tides run especially high and low. And when they sit at right angles across the sky, their effects partly cancel, and the tides are milder. So, the sea keeps a slow monthly rhythm as well as a daily one, rising and falling in gentle time, with the changing dance of the Sunday and moon around us. For most of history, people watched these rhythms with wonder and could only guess at their cause. Some sensed that the moon was somehow behind the pattern, since the tides kept such faithful time with it, and yet the two high waters each day, one under the moon and one facing away from it, stayed a genuine puzzle. Only the idea of a difference in the curve of space across the whole body of the Earth makes the double rhythm simple and clear. The tide that most ordinary of coastal sights turns out to be a daily, visible sign of the very thing we have been chasing all along. The way the shape of space changes from one place to the next. There is a deeper wonder hidden in the tides, and it takes us right back to the falling room. Remember that inside a small sealed room in free fall, everything floats and gravity seems to switch off completely. But now imagine a very tall room, tall enough that its top and its bottom sit in noticeably different parts of the curve of space. The bottom, deeper in the well, falls a little faster, and the top, higher up, falls a little slower. And so two objects placed at the two ends will slowly drift apart as the room falls. This gentle stretching is the tide, and it is the one part of gravity you can never make vanish. And this is why the tides matter so much to the whole idea. Free fall can hide the simple pull of a world entirely, so that inside a falling room you would swear there was no gravity at all. but it cannot hide the difference in the curve from one place to another. That difference is the true, unhideable signature of gravity as the shape of space, the thing that remains when everything else has been smoothed away by falling. The sea rising softly on two shores at once is the most familiar face of the deepest truth in this whole journey. From here, we drift out to the maker of those tides and to the long, patient fall of the moon itself. Lift your gaze now to the moon, that calm grey companion that has circled us since long before there were eyes to watch it. We have already seen that the moon is not held up by anything, and that it is not resting on some invisible shelf in the sky. It is falling exactly as an apple falls, coasting along the straightest path it can through the curved space around the Earth. The only reason it never arrives is that it is also sweeping sideways, fast enough that its fall carries it around the curve of our world instead of down onto it, and so the moon has been falling toward us for billions of years, and it has been missing patiently all that time. There is a quiet intimacy between the moon and the Earth that the tides help to explain. Long ago, the moon turned more freely, showing us many faces as it went. But the same gentle stretching that raises the tides in our oceans also worked over vast stretches of time on the body of the moon itself, slowly easing its spin until it settled into a calm rhythm. Now the moon turns exactly once for every time it circles us, so that it keeps one steady face toward the Earth forever. The far side of the moon never turns to greet us. It is a patience so complete that we saw it for the first time only when we sent machines around the back to look. This settling into a single steady face is a gift of the same tides that lift our seas, working slowly on the body of the moon itself. Long ago, when the moon turned more freely, the Earth raised gentle swells in the moon's own material, just as the moon raises swells in our oceans. Those swells acted as the softest of breaks, easing the moon's spin down over vast reaches of time, until it settled into the calm rhythm we see now, turning once for each time it circles us. Many of the moons that orbit the other planets have settled the very same way, each keeping one quiet face turned forever toward the world it falls around. It is one of the most common and gentle outcomes of the shape of space. So the moon and the Earth have fallen into a kind of quiet companionship, the two of them locked in a slow, steady turn. The moon showing us one patient face and drifting a fraction of an inch farther out each year. None of it is hurried, and none of it is forced. It is simply what happens when two worlds fall around each other for long enough, gently trading the tides between them, settling into balance. The next time the moon hangs full and bright above your roof, you might remember that you are watching a fall billions of years old, and a face that has been turned toward us faithfully for longer than there have been eyes to meet it, and the exchange runs both ways in a slow and tender balance. As the Earth's oceans are lifted into their two swells, the turning of the Earth drags those swells a little ahead of the moon, and their small extra tug gives the moon a gentle forward nudge on every orbit. That nudge, repeated for age upon age, is very slowly lifting the moon into a wider orbit, carrying it away from us by about 1.5 inches each year. It is a departure so gentle that no one will ever feel it, a widening measured against the lifetime of the whole world. The moon rises away from us at about the speed your own fingernails grow. Rest for a moment in the sheer patience of it. The moon falls toward the earth without cease, and misses without cease, and drifts outward by the width of a breath each year. And all of this has been going on quietly overhead through every night that ever was. When you look up at the moon, you are watching an endless, gentle fall that has never once touched bottom, held in the same curved shape of space that holds you softly to your bed. The same idea that presses you into the mattress keeps the moon aloft in the sky. There is one shape, and everything rests within it. And this raises a gentle question that will carry us deeper still. If the moon stays aloft by falling sideways fast enough to keep missing the earth, then how fast would a thing have to travel to leave the curve of a world behind altogether, to climb up out of the valley and never roll back down? That question has a calm and beautiful answer, and following it will lead us to the deepest valleys in all the universe, places where the curve of space grows so steep that not even light can climb back out. From here, we drift toward what it takes to leave the well. Toss a ball gently upward, and it rises a little way, slows, stops, and comes back down into your hand. Throw it harder, and it climbs higher before it turns and returns. In the picture we have built tonight, the ball is rolling a little way up the inner slope of the Earth's valley in space, losing its pace as it climbs, until it can rise no farther and rolls back down. Everything you throw upward is simply running partway up the side of the well before the shape of space brings it home again. The harder you throw, the higher up the slope it reaches before returning. Now ask the natural question, is there a speed fast enough that the ball would climb the slope and simply never come back? There is, and it has a calm name, the escape speed. For the Earth, it comes to about 7 miles in every second, a pace almost beyond imagining, far swifter than any sound. Hurl something upward that fast, ignoring the air, and it will climb the slope of the well forever, always slowing, but never quite stopping, coasting on and on into the space between the worlds without ever turning back. That is what it means for a rocket to reach for the planets, to run fast enough up the valley wall to leave it behind. The escape speed depends entirely on how deep the valley is, and the depth depends on how much matter has gathered to carve it. A small light world makes only a shallow dip in space, and it takes very little pace to climb out. But a large, heavy world carves a deep, steep well, and the climb demands a far greater speed. On a small moon you might leap upward and rise for a long, slow while. But on a giant planet the same leap would barely lift your heels. The deeper the curve of space around a world, the harder anything must run to escape it, and the more firmly the world holds its sky and seas in place. This is why our own world keeps its air, and it is a gentle thing to picture. The molecules of the atmosphere are always in motion, drifting and bouncing, and now and then one near the very top is moving upward quite fast. But the Earth's valley in space is deep enough, and the escape speed high enough, that almost none of them can climb all the way out. So the air stays, gathered in a thin, soft shell around the planet, held not by a lid but simply by the depth of the well. A smaller world, with a shallower valley, cannot hold its air so well, and lets it slip away into space over long ages. The sky itself is a thing kept close by the shape of space, and this is what every journey away from the Earth must reckon with. To send a craft to the moon or the planets, we must give it enough speed to climb far up the valley wall, or even to leave the valley altogether. And that is why the great machines that carry travelers upward must work so hard and burn so long. They are not fighting a downward pull so much as running up a slope in the shape of space, trading their fierce speed for height against the curve. Once they reach far enough and fast enough, they coast, falling freely again along the shape, drifting the long quiet distances between the worlds with their engines still and silent. So let your thoughts follow the slope downward now into ever deeper valleys. Picture a place where so much matter has gathered into so small a space that the well it carves is not gentle at all, but steep beyond all others, plunging down and down. As the valley deepens, the speed needed to climb out of it grows and grows until you reach a point almost past belief. You arrive at a well so deep that the escape speed rises all the way up to the speed of light itself. And light, for all its swiftness, cannot go faster than light. From here, we drift softly to the edge of those deepest valleys, where even light must stay. In the deepest valleys of the universe, the curve of space becomes so steep that nothing which enters can climb back out, not even light. We call these places black holes, and though their name can sound severe, seen through the calm idea we have built tonight, they are simply the most extreme form of the same gentle thing, a well in the shape of space, carved so deep that its walls have closed over the top. Around each one lies an invisible boundary, a smooth spherical edge we call the horizon, and it marks the place beyond which the slope is too steep for any return. A black hole does not reach out and grab at the space around it. Far away from one, the curve of space is as gentle as the curve around any ordinary star, and a planet could circle it calmly for ages, coasting along its orbit exactly as the Earth coasts around the Sunday. It is only as you draw very near that the valley steepens, and the pace needed to climb away grows toward the speed of light. At the horizon itself, that pace reaches the speed of light exactly, and just inside it, the slope tips beyond even light's great swiftness. Light that crosses that edge simply follows the curve inward, along the steepest path there is, and does not come back to us. These deep valleys are carved in the quietest way imaginable, at the end of the long life of the greatest stars. A truly massive star spends millions of years shining, holding itself up against its own weight, with the heat of its core. When at last its fuel is spent, and its core can hold itself up no longer, it collapses inward, folding an enormous amount of matter into a space, smaller and smaller, until the curve of space around it has become one of these steepest of all wells. What remains is calm and dark, and almost perfectly round, a smooth, deep dimple in the fabric of the cosmos, resting quietly among the stars. Some of these deep wells are far grander than any single star could carve, and they sit at the very hearts of the galaxies. In the center of our own great island of stars, and of nearly every other, rests one of these enormous dark wells, holding the weight of millions of suns folded into a region we could never see across. Around it, whole crowds of stars wheel in long, slow orbits, coasting through the deep curve it makes in space, circling the calm, dark center for hundreds of millions of years at a turn. These giant wells are not chasms tearing at the galaxies. They are the still, deep centers around which the great pinwheels of stars quietly turn. For a long time, these places were known only through the idea itself, through the shape of space, demanding that such wells could exist. But we have gathered them into view in recent years, watching stars swing in tight, fast loops around an unseen center, feeling the ripples of two of them merging, and even gathering the faint ring of light that bends around one to make a soft glowing halo about a round patch of dark. Each of these is another quiet confirmation of the same gentle idea we began with in a falling room. A black hole is not a thing apart from the rest. It is the deepest note of the very same music, the shape of space, carried to its farthest and calmest extreme. Set aside the fearsome stories for a moment, and these places show themselves as they truly are, deeply peaceful. A black hole makes no sound and casts no light of its own. It simply sits, a region where the shape of space has folded over on itself, holding whatever has fallen in with the same silent patience that holds the moon in the sky and holds you softly to your bed. The light of distant stars, passing near, bends smoothly around the dark sphere and travels on, drawing a bright thin ring in the sky. Even at the deepest bottom of the deepest valley, there is only the same calm rule we have followed all along. Things quietly taking the path the shape of space allows. And these deepest valleys hold one more gift for us, one that took 100 years to gather and catch. When two of these great dark wells fall toward each other and begin to circle closer and closer, faster and faster, they stir the very fabric of space and time so strongly that they set it trembling. The shape of space itself begins to ripple, and those ripples spread outward across the universe like rings on a still pond. From here, we drift outward along one of those ripples and listen to the sound of space itself, gently ringing. If space and time can be curved and shaped, then they can also be stirred. And this is one of the loveliest predictions of the whole idea. When very heavy objects move sharply, especially when two of them whirl around each other in a tightening spiral, they do not simply sit in the curved space they have made. They shake it. Out they send ripples, gentle waves in the shape of space itself, that travel outward in every direction at the speed of light. As each ripple passes through a region of space, it stretches that region ever so slightly in one direction and squeezes it in another, then lets it spring softly back. These ripples have a name of quiet music, gravitational waves, and Einstein predicted them within his idea long before anyone could dream of catching one. The trouble was that the stretching they bring is almost unimaginably small. By the time a ripple born in the depths of the cosmos reaches the Earth, it squeezes and stretches space by less than the width of an atom across the width of a whole planet. To feel a shiver that faint seemed, for a very long time, entirely beyond us. The waves were a beautiful thought that might forever stay only a thought, a trembling of space too slight for any hand to hold. And then, in the year 2015, we caught one. Patient builders had laid out enormous, exquisitely still instruments, long straight tunnels stretching for miles, with beams of light running down them to measure their length with a precision almost beyond belief. On a September morning, those instruments felt a single gentle shiver pass through them, a stretch and a squeeze, exactly matching the shape of a passing gravitational wave. It had come from two black holes, more than 1 billion light years away, that had spiraled together and merged into one. sending out a last great ripple across the shape of space. The shape of that first captured ripple told a whole quiet story if you knew how to read it. As the two dark wells spiraled closer, they circled faster and faster, and the ripples they sent out rose in pitch, like a note sliding upward, quickening in the final moments, before the two became one. Then, as they merged into a single larger well, the trembling settled, ringing down softly like a struck bell, fading into silence. Scientists could translate that pattern of stretch and squeeze into sound, and what came out was a faint, brief rising tone, followed by a gentle fade, the actual voice of two distant wells becoming one, carried to us across 1 billion years of dark. Since that first gentle shiver, we have felt many more, and each one is a small window opened onto events we could never have seen by light alone. Two of these deep wells, joining far across the universe, give off almost no light at all, and yet they shake the fabric of space so strongly that their ripple can cross the whole cosmos and still be felt. So we have gained a new sense entirely, a way of feeling the universe tremble rather than only watching it shine. The sky, once known only through the light that reaches our eyes, now also speaks to us in the faint, slow ringing of its own shifting shape. Let the scale of that gentle arrival settle over you. The two dark wells that made the wave had circled and merged before the earth had oceans, before the Sunday had formed in a corner of the universe more than 1 billion years away by light. Their final ripple set out across all that space and time, spreading and thinning as it traveled, crossing the emptiness between the galaxies for 1 billion years, until at last it washed over our small world and moved a beam of light by less than the width of an atom, and we felt it. We had learned to sense the trembling of space itself, the faint far ringing of the shape of things. There is a deep calm in knowing this. The universe is not a rigid stage on which things happen. It is a soft, responsive fabric, curved by every mass within it and able to tremble and ring when that mass moves. Space and time bend around the earth to hold you gently to your bed. They slope through the sky to keep the moon aloft. They plunge into the deepest valleys around the darkest stars, and they shiver ever so faintly with the passing of ripples born in the far reaches of time. It is all one fabric, one shape, one quiet idea, from your own weight to the ringing of the distant cosmos. From here, we drift back toward home and toward one last and gentle truth about how all things fall together. As we begin the long turn homeward, let us gather the whole journey into a single quiet thought, one that may be the most restful of all. Everything in the universe is falling. Not a few things, not the apple and the space station alone, but truly everything, all of it everywhere, is in a state of gentle, endless free fall. The moon falls around the earth. Earth, together with the moon, falls around the Sunday, coasting along its great curved orbit through the valley. The Sunday has carved in space. Nothing up there is being pushed along its path. It is all simply following the shape, and the falling does not stop with the Sunday. Our Sunday, carrying the Earth and all the planets with it, is itself falling, sweeping in a vast slow circle around the distant center of our galaxy, a journey so wide that a single loop takes far longer than there have been living things on Earth. The whole solar system coasts together through the curved space of the galaxy, a small raft of worlds falling endlessly around a center it will never reach. Everything we know Every place any of us has ever stood is riding along on that immense, silent, effortless fall through the shape of space. Wider still, the galaxies themselves are falling. Our own vast island of stars is drifting toward its great neighbor across the emptiness between them. The two of them slowly coasting closer along the gentle curve their combined weight has shaped. In a fall so unhurried, it will not gather them together for billions of years. Across the whole visible universe, clusters of galaxies lean and drift toward one another, each one coasting freely along the shape that all the matter within it has made. There is no great engine anywhere, no vast hand pushing the cosmos along, only shape and the endless, gentle falling of everything through it. Hold all of these falls together in your mind for a moment, nested one inside another, like a set of gentle wheels within wheels. You rest on the earth, which turns as it falls around the Sunday. The moon falls around the earth as both of them fall around the Sunday. Our Sunday falls around the heart of the galaxy, carrying the whole family of planets along, and the galaxy itself drifts and falls through the wider dark toward its neighbors. Every one of these motions is a free fall along a curve, a coasting with no effort and no strain, each nested softly inside the next, all the way from the weight in your own limbs out to the slow wheeling of the galaxies. And here is the quietest wonder of all to carry into sleep. You feel perfectly still right now, lying in one place, going nowhere. Yet you are being carried at once through several of these great falls, turning with the earth, sweeping around the Sunday, drifting with the whole Sunday around the distant galactic center, all without the faintest sensation of motion. There is no wind, no rush, no sense of speed, because you are in free fall along with everything around you, and free fall feels like perfect rest. The deepest, fastest journeys of your life are the ones you take lying utterly still, carried in silence along the gentle shape of space. Rest in how peaceful that picture truly is. The entire universe, from the moon overhead to the farthest cluster of galaxies, is doing exactly one thing, quietly and without strain. And it is the very same thing your own body does the instant a floor is taken away. It is falling freely, following the curve of space, with no effort at all. Falling is not a struggle, and it is not a plunge into anything to be feared. It is the most natural and restful motion there is. The motion of a thing perfectly at ease, going wherever the shape of the universe gently invites it to go. All of creation is drifting, weightless, along that invitation. And so, having drifted out to the ringing of distant space and back again, we return to a small and human image to close the circle. If everything falls the same, if the apple and the station and the moon and the galaxies all coast alike along the curve of space, caring nothing for their own weight, then the very lightest and the very heaviest things must fall together as perfect equals. To see that with your own eyes, we come down at last onto the still grey ground of the moon, where a person once held out a feather and a hammer against the black sky. From here, we drift down one last time to watch a feather and a hammer fall together on the moon. There is one more quiet wonder that the shape of space explains, and it is one people have puzzled over for a very long time. Drop a heavy stone and a light pebble from the same height, and, if you set aside the drag of the air, they land at exactly the same moment. This seems to make no sense at first. Surely the heavier object, feeling a stronger pull, should hurry to the ground ahead of the lighter one, and yet it does not. a cannonball and a marble, released together in a room emptied of air, come down side by side and touch the floor as one. The reason puzzled the great thinkers of the past, and it was Galileo, 4 centuries ago, who first argued clearly that all objects fall at the same rate, regardless of their weight. In the old picture of gravity as a pull, this required a delicate coincidence. A heavier object is indeed pulled harder, but a heavier object is also more reluctant to be moved, more sluggish, harder to get going, in exactly the same proportion. The stronger pull and the greater reluctance cancel out perfectly, and every object, heavy or light, accelerates downward at precisely the same rate. In Newton's picture, this perfect balance was true, but no one could quite say why it should be so exact. People have made this equal falling visible in a simple and lovely way, with a tall glass tube and a pump. Place a coin and a feather inside the tube and turn it over, and the coin drops at once while the feather drifts and sways slowly down long after. But now draw all the air out of the tube until there is nothing inside to slow anything, and turn it over again. This time the coin and the feather fall together, side by side, touching the bottom at the very same instant. The only thing that ever made them differ was the air pushing against the feather. Take the air away, and the shape of space treats the coin and the feather as perfect equals. There is a plain beauty in why this must be so. Once you see falling as following a shape. If a heavy thing were truly pulled harder, you might expect it to win the race to the ground. But in the picture of curved space, nothing is pulled at all, and so there is no race to win. Every object simply coasts along the curve of space and time, and the curve is the same curve for all of them, caring nothing for how much matter each one carries. A boulder and a grain of sand set loose together roll down the very same slope, along the very same path, and arrive as one. The shape does not weigh its travelers. It only offers the way and lets everything take it alike. Einstein's picture makes the mystery dissolve, and this is perhaps its most graceful gift of all. If there is no pull, then there is nothing to balance. Objects, in free fall, are simply following the curved shape of space and time, and the shape does not care in the least how heavy the traveler is. A great boulder and a single grain of sand set loose at the same spot roll down the very same slope of curved space along the very same path, and so they fall together. It is exactly like two balls of different sizes released on the same smooth hillside. The hill does not ask their weight. It only offers its shape, and everything follows it alike. This is not a thing we merely believe. It has been shown, of all places, on the surface of the moon. Standing there in 1971, with no air at all to slow anything, an astronaut held out a feather in one hand and a heavy hammer in the other, and let them go at the same instant. On Earth, the feather would drift and flutter and settle long after the hammer. But on the airless moon, with nothing to resist them, the feather and the hammer fell together, touching the grey dust at the very same moment. The whole world could watch the shape of space treat a wisp and a weight as perfect equals. Let that gentle image stay with you as we begin to turn homeward. A feather and a hammer, as different as two objects could be, falling as one, because falling is not about weight at all. It is about the shape of the space they move through, a shape that offers the same path to everything, the lightest and the heaviest alike, asking nothing, forcing nothing, simply curving and letting all things follow. There is a deep calm in that fairness, in a universe that lets the feather and the hammer arrive together. From here, we drift the last of the way back to your own quiet weight against the bed and what it has really been all along. So we come gently back to where we began, to the simple feeling of being heavy against the surface that holds you. All through this journey, we have circled one quiet reversal, and now we can say it plainly. You have never once felt gravity. Not tonight, not ever, not for a single moment of your life. Gravity, the true thing, is the silent curving of space and time, and a curve is not something a body can feel. What you feel always is the surface that stops you from following it. The bed, the floor, the ground, pressing up to hold you out of your fall. Think of everything that feeling has really been. The heaviness in your limbs at the end of a long day is the mattress pushing up along the length of you. That pressure in your feet when you stand is the floor pushing back. A reading on a scale is only the push between your body and its surface. In every case, without exception, the sensation you named gravity was the touch of something solid refusing to fall with you, holding you gently in place, one curve above the bottom of the Earth's great smooth. Well, the pull you imagined has been a push all along. Turn that thought over once more gently, because it changes the feeling of your own bed. The weight settling you into the mattress right now is not a hand reaching up from the center of the planet to hold you down. It is the mattress itself, pressing up against you, stopping you from following the gentle slope of space toward the ground. You are being held, not pulled, cradled by the surface beneath you, against a fall you cannot even feel. There is a great softness in that, in knowing that the heaviness of your own body is really the tender push of the world, keeping you afloat near the top of its valley while you rest. And it means that the deepest experience of gravity is not heaviness at all, but its opposite. To truly meet the pull of the earth, to give yourself over to the curve of space completely, would be to feel nothing whatsoever. To drift as the astronauts drift, as the moon drifts, as everything in the sky forever drifts. The falling we quietly fear turns out to be the most restful state there is. The state of a thing that has stopped resisting and simply follows the shape of things. You need not fear that fall tonight, and you need not take it. The ground will hold you softly where you are, and you may simply rest. And now you know what the true pull would feel like, if you could ever feel it. It would feel like nothing. Step off into a genuine free fall, with no floor beneath you and no seat behind you, and the entire sensation of weight would simply melt away because there would be no surface left to press against you. In that moment, you would not be leaving gravity behind. You would be surrendering to it completely, following the curve of space at last, moving exactly as the shape of the universe invites every free thing to move. The truest experience of gravity is the quiet absence of any feeling at all. There is a great gentleness in seeing it this way. The earth is not gripping you with a fist that reaches up from its core. It has simply shaped the space around itself into a wide, soft valley, and you have come to rest near the bottom of it, held by the ground from sliding any deeper. Nothing about you is being forced, nor are you straining against a pull. You are lying in a curve, a gentle bend in space and time carved by the whole vast weight of the world, and the ground beneath you is only keeping you company at the bottom of the ball. Let the whole idea settle over you now like a blanket. The pull you thought you felt was a shape. Your weight is really a push. That falling you feared is the freest and most natural motion there is, the motion of a thing finally left alone. And the ground that holds you, night after night, is simply the kind surface at the bottom of a valley in space, keeping you gently from a fall you will never need to take. There is nothing here to hold on to and nothing to solve. Only the quiet shape of the universe, and you, resting easily within it. From here, we drift the last soft distance home. We have come a long, slow way tonight, and now the journey folds quietly closed. It began with the weight of your own body against the bed, and the feeling that something was pulling you down. From there, we drifted through a falling room where weight vanished, past a station forever falling and missing the earth, up to clocks in the sky that tick a little faster than the clocks in your kitchen, out to light bending around distant galaxies, and down at last to a feather and a hammer falling together on the moon. And every step led back to the same soft truth, that gravity is not a pull, but the gentle shape of space itself. So there is nothing left for you to do now but rest. You are lying in a curve of space and time, a shallow valley carved by the world beneath you, and the ground is holding you softly at its floor. Nothing is pulling you down, and nothing is making you fall. You are simply being held, the way a stone is held in an open hand, resting in the shape of things. Let your thoughts grow slow and far away, and let the quiet of the deep sky settle over the room, cool and calm and endless. There is nothing left tonight that asks anything of you. The moon overhead keeps up its long, patient fall. The satellites trace their quiet rings. The far galaxies drift toward one another, across unimaginable gulfs of dark, and all of it moves without the least effort, carried along the gentle shape of space just as you are. You are part of that same calm motion, held in the same soft curve, resting near the bottom of the same wide valley the whole world lies within. Let each breath grow a little slower than the one before, and let the weight you feel be simply the kind and steady push of the bed holding you while you drift. If this slow journey brought you any peace, you might let it stay with you again on another night. And there are more of these quiet voyages waiting whenever sleep is slow to come. But there is nothing you need to do with that thought now. Whatever weight the day set upon you, you may set it down here at the bottom of the gentle valley, and let the shape of the universe hold it for a while. Rest now, easy and unhurried, in the cool, luminous deep. The stars will keep their slow watch, and the quiet will stay with you. Good night.